Hi everyone. Thank you for attending the BAS Electrochemical Webinar 2020 Autumn. I'm Miho, representing BAS Inc. International Sales Team, and I will be the moderator. Before we start, we will ask you to don't be worried to record and enjoy the webinar. We are recording, and we will send the direction to you as soon as it is ready. In this way, you will be able to review the full webinar. Also, if you have any question, please feel free to contact us. Well, let's start the webinar with the lecture. Dr. Shen, her topic is Basics of Hydrodynamic Voltammetry and Application.
Welcome to BAS Webinar 2020 Autumn. My topic is in Basics of Hydrodynamic Voltammetry Measurement and Application. The contents are shown here. Please refer to this page. As an electrochemical reaction is a heterogeneous reaction involving mass transfer process of chemical species in solution and the electron transfer process at electrode surface. In general, it proceeds through three elementary steps. 1. Substrate mass transfer to the electrode surface. The electrode transfer in the electrode surface. The product diffusion from the electrode. Electrode reaction rate. The current is considered to be controlled by the slowest process, the rate-limiting process. Electron transfer process and mass transfer process are the main factors affecting the electrode reaction rate. In a slow electron transfer rate reaction system with sufficient transport capacity, the electron transfer process determines the electrode reaction rate. On the other hand, in a fast electron transfer rate reaction system, the mass transport rate determines the electrode reaction rate. Thus, no matter how the potential increased, the current is no longer increased. This saturated current is called the limiting current, which is due to transport capacity of reactant to the electrode surface has reached its limit. Considering the case which the mass transport is rate limiting, there are three methods of mass transport process: convection, diffusion, and migration. When using a high concentration supporting cell, mass transfer by migration is most negligible. Convection and diffusion are the main transport method of reactant to the electrode surface. During the convection voltammeter measurement, if the solution is stirred, the flow of the solution is not stable, so it is difficult to mathematically analyze the transport rate. The hydrodynamic voltammetry RD and RD measurement introduced today is a forced convection voltammetry that can quantify mass transport on the electrode surface. Electrode rotating in solution may control the thickness of diffusion layer near the electrode surface by forced convection. The higher the rotation speed, the faster the convection of the solution, and as a result, the diffusion layer becomes thinner and the diffusion speed increases. That is, the diffusion speed of a reactant and the products can be controlled by the electrode rotation rate. The Nernst diffusion layer model is used to analyze mathematical mass transport. The thickness of diffusion layer can be calculated with the equation 2.1.1. The mass transfer coefficient is defined as the diffusion coefficient divided by the diffusion layer thickness as shown in 2.1.2 equation. The current value is proportional to the concentration gradient. When the electrode surface concentration of the reactant becomes zero, the concentration gradient becomes maximum, at which time the diffusion limiting current is obtained. Substituting above concentration equation into the Nernst equation, the current potential curve is expressed by equation 2.1.4. When mass transfer coefficient of redox substance are the same, the half-wave potential is corresponding to the redox potential. The half-wave potential can be easily determined from the RD measurement. From these equations, the diffusion limiting current Levitch equation can be obtained and indicated here. By plotting the diffusion limiting current against the square root of the rotation angular velocity, a linear Levitch plot can be drawn. From the slope of the plot, electrochemical parameters such as number of reaction electron, diffusion coefficient can be obtained. Device and equipment required for RD measurement are shown in here. A to D are also used in popular EC measurement. E, F, G are specially needed for RD measurement. A reaction system in which the electron transfer rate on electrode surface is sufficiently fast than the diffusion rate of the reactant is called a reversible system. The redox reaction between Felician and Felicia is a typical example. For experiment, first prepare electrolyte solution as shown here, and next set up the rotating electrode to the RD3A rotator, following below procedures. RD cell setup procedures are shown in this here and these pictures. The next step is to connect and configure the electrode rotator and potentiostat. Here is the connection on the back panel of the RD3A and the Model2325 Bi-Potentiostat. On the right side is the RD3A AC cable terminal, power switch, ground terminal, and a gas inlet. From here, external gas enters from here and come out from the gas purge tube in the front of the RD3A. This is the rotation speed control terminal, and this is the gas purge time remote control terminal. If they are connected with a remote control cable to Model 2325 I/O port, the rotation speed and purge time can be remotely controlled by Model 2325 software. For the manual control, no need to connect this cable. Connected the potentiostat lead wire to RD lead pin of RD3A reference electrode and a counter electrode. After bulb preparation, make sure there are no gas air bubble in the reference electrode liquid junction and the disc electrode surface. For successful RD measurement, the used RD electrode should be in good state. It is recommended to check RD electrode with CV measurement at slow potential sweep rate such as 2510 5 mV per second. If the CV data may meet with below features of the reversible system CVs, the RD electrode is usable. Otherwise, The electrode should be polished or electrochemically cleaned and checked again. The conditions for hydrodynamic voltagram measurement using linear sweep voltammetry are shown here. The potential sweep rate is 10 mV per second. The potential sweep range is from 0.6 volt to minus 0.1 volt. RD3 rotation speed is set to, for example, 500 RPM. Confirm the steady rotation by rotating the electrode. Run the RLSV and record the voltagrams by potential sweep to negative direction under the different reaction rate. Here shows the method for obtaining diffusion limiting current and half-wave potential. The usual processing method is to draw 3 tangent lines as shown in here. A vertical line is drawn from intersection to obtain the diffusion limiting current. Model2325 software automatically displays the diffusion limit current with such fitting when peak definition is set to sigmoid. Two methods give out almost the same limit current and half-wave potential. If the diffusion limiting current under the various rotation speed obtained by automatic processing of the software are plotted against the square root of the rotation angular velocity, the linear Leverage plot can be drawn. By substituting these parameters into the slope of the plot of the Leverage equation, a diffusion coefficient of ferrocyanide ion in this solution is calculated for this value. Model 2325 has Leverage plot data analysis function. In its F-plot window, overlay the RD data. Select the Leverage plot function. Select the method to leverage. Enter the potential for the limiting current selection. A linear plot appears and the slope is shown in here. Furthermore, select the parameter to calculate, such as D. Enter the value of other parameters. Click the Update button. D is calculated and displayed immediately. A reaction system in which electron transfer occurs slowly on the electrode surface is called an irreversible system. A typical reaction is the oxygen reduction. In an alkaline solution, oxygen undergoes 2 or 4 electrons reaction, depending on the electrode material. The Kotek-Leverage equation is used for the irreversible reaction system analysis. In the case of electrocatalyst, the reaction electron number NAPP of the catalytic reaction can be obtained from the slope of the Kotek-Leverage plot. RD experiment for oxygen reduction reaction in alkaline solution is carried out by using the electrolyte solution indicated here. Potential sweep range is from 0.05 volt to minus 1.25 volt. Potential sweep rate is set to 10 mV and the LSV voltagram is recorded by potential sweep to negative direction. At a certain potential, the reciprocal of the current value is plotted against the reciprocal of the square root of the rotation angular velocity omega. A linear relationship is obtained. The number of oxygen reduction electrons can be calculated from the slopes of the plots. Dissolved oxygen concentration, oxygen diffusion coefficient, kinematic viscosity of the solution, electrode surface area, Faraday constant, as shown in here. If use Model2325 Bi-Potentiostat for RD measurement, the cortic lavage plot data analysis will be quick and easy. Overlay the RD data in fplot window, select the lavage plot function, then select the method to lavage cortic K-lavage. Input the potential, enter the potential for the current selection, and the linear plot appears, then the slope and the intercept are displayed. Furthermore, select parameter to calculate such as n, enter other parameter value, click the update button, the n is calculated immediately. This function is quite helpful for each parameter calculation. When this RD electrode used, the RD measurement can be carried out. The disk electrode is in the center, and a thin layer of insulator and the ring electrode are placed around it, and the surrounding area is covered with an insulator outer cylinder. The fundamental rotating features of RD are similar to RDE. By adding a ring electrode surround the disk electrode, the oxidative species force generated on the disk electrode is transported by centrifugal force to the ring electrode and detected at the ring electrode. Analysis of ring electrode current provides the information about the product and the intermediates of the disk electrode reaction. The rotating electrode method is often used in the field of fuel cell research, especially in the case of polymer electrolyte fuel cell (PEFC), as shown in here. The influence of the electrolyte membrane contained in the battery, the gas diffusion layer of the fuel cell, and the activity of various electrode catalysts can be evaluated by using RD measurement. These are the essential equipment required for RD measurement. The electrode rotation is controlled by RD3A rotator. A bi-potentiostat, such as Model2325, may control the potential of the ring and disk independently by referring to a single reference electrode, and record the ring and the disk current, which fall into same counter as shown in here. Here, please pay much attention to the RD electrode and the cell used. The electrode surface of ring and the disk must be uniform and the same plane. The disk and the ring electrode have no eccentricity. Once there is eccentricity, the capture rate differs greatly from the theoretical end value. The cell diameter inside is about 5 times the outer diameter of the electrode as a guideline. A large diameter cell is necessary to prevent turbulence and the high rotation speed. In order to perform a quantitative RD measurement, it is necessary to understand the substitute mass transport situation from disk electrode to ring electrode. The typical parameter is the correction efficiency, N. If the below reaction occurs on the disk and the ring, the reductive species formed in the disk electrode can be detected as a ring current. However, a part of reductive species may escape to the bulk during transport from the disk electrode to the ring electrode, and the disk current absolute value ID is larger than that of the ring electrode. A real correction efficiency is defined as the ratio of the ring current and the disk current. The theoretical correction efficiency is a constant determined only by the dimensions of both electrodes and can be calculated using these theoretical equations. If AS are the electrode, R1, R2, R3 value are used for this equation, the calculated value is n equal to 0.424. Because an real electrode surface is uneven, the real correction efficiency is harder to be coincidence to the theoretical value. Usually, reversible systems indicated here may be used for RD electrode correction efficiency measurement. Let's see an example for correction measurement. The electrode solution, disc electrode and ring electrode applied potential are shown in here. The theoretical correction efficiency is 0.424. The left figure A shows the RD measurement results under various rotation rates. The disc currents are in upper side and the ring currents are in downside. The right figure B shows the ratio of IR to ID is almost constant under various rotation speed. The average of the coefficient correction efficiency N is 0.4224. This value is quite near to the calculated N value 0.424. Finally, let's see RD experiment for oxygen reduction reaction in alkaline solution. The electrolyte solution, potential sweep range in disc electrode, RD measurement conditions are shown in here. Oxygen saturated 1 mole per liter sodium hydroxide oxygen solution is obtained by purging the oxygen gas for about 20 to 30 minutes with purge time control of RD3A. Right side shows the measured RD data of disc and the ring. For easy viewing, the disc current and the ring current are displayed in separate graphs. Generally, in carbon-based electrode, the reaction that occurs at the disc electrode in an alkaline solution is shown by the above formulas. First, a two electrons reaction of oxygen occurs, and when the potential is further swept to the negative direction, a 4-electron reaction occurs and the current increases and the second wave is seen. In the ring, the potential is set to 0.1 volt for sufficiently oxidizing hydrogen peroxide ion, and the generated oxygen peroxide ion are oxidized and detected by the ring current. Corresponding to the disc electrode potential of minus 0.5 volt, the current increased corresponding to the first wave of the ring electrode at that time. But the ring current decreased near the disc potential of minus 1 volt. From this, it can be seen that the hydrogen peroxide ion generated at the disc electrode undergoes a further 2 electron reaction and a part of the generated hydrogen peroxide ion is reduced to the hydrogen ion so that the ring current decreased. In other words, by the ring electrode detecting the disc electrode, the reaction product and mechanism can be elucidated. Furthermore, from the ring and the disc electrode current obtained by RD measurement, the number of oxygen reduction reaction electrons of the disk electrode catalyst, and the generation rate of hydrogen peroxide can be calculated by these equations. For example, using the ring and disk electrode current of the RD measurement at 2400 rpm, we calculate by substituting them to this equation. The number of oxygen reducting electron at minus 0.5 volt is 2.9, and the rate of hydrogen peroxide generation is about 53.7%, and at minus 1 volt, the number of reaction electron is 3.2, and the rate of hydrogen peroxide generation is 37.7%. Of course, this result is not ideal, but in this paper, they use an H-surface pyritic graphite disk electrode, platinum ring electrode, and succeeded in a 4-electron reaction. Some results are shown here. Thank you for your attention.
Thank you, Dr. Shen. In the technical note on the ALS website, you can find some extra references written by her. In addition, in the technical note, you can find explanatory material on the electrochemical and spectroelectrochemical research field. And some topics are discussed here on the BAS channel, which you can follow and have access to the latest news. Next, Mr. Takeshi Inamori. His topic is Difference Electrode Potential Calibration.
Hi, I'm Takeshi Inamori, International Sales of BAS Inc. Thank you for your time today. Alright, I'll get started the title of Reference Electrode Potential Calibration. Here's the index of today. Today, we'll show one of the fundamentals of electrochemistry, reference electrode. We'll show you some representative types of reference electrodes. We'll also introduce a newly released H2D1 portable hydrogen generator to you. For an electrochemical measurement using potentiostat, the general configuration of 3 electrode cells is shown here. The electrochemical reaction happens at the surface of the working electrode. Reference electrodes are the benchmark for the potentiostat controlling the potential of the working electrode. Here are types of reference electrodes. The primary type is hydrogen electrodes. The secondary type is consisting of metal and its insoluble salt, such as caramel, silver chloride. BAS Inc. offers these 2 types of reference electrodes in our reference electrodes lineup. We'll show the details in the next slide. Reference electrodes are the benchmark of the potential applying to the working electrodes. The potential of reference electrodes should have high stability and reproducibility. The electrode potential is following the Nernst equation. E Standard electrode potential is the equilibrium electrode potential at 25 degrees Celsius, which AO, the oxidative state species activities, and AR, the reactive state species activities, are equal to 1 molar. This kind of relationship is well known. The primary type of reference electrodes is the standard hydrogen electrode, SHE. This means we bubble hydrogen gas at 1 atmosphere across the platinum electrode in an acid solution. Hydrogen gas can either be oxidized to form hydrogen ions, or hydrogen ions can be reduced to form hydrogen gas. This potential is defined as being zero potential. However, it is not necessarily convenient for daily use because of troublesome handling of hydrogen gas. Reversible hydrogen electrode is one of the primary type reference electrode. The potential of RHE depends on the hydrogen gas pressure and the hydrogen ion activity in the inner solution. When 1.2 molar hydrochloric acid at 25 degrees Celsius is used, the hydrogen ion is theoretically calculated to be 1. The electrode potential will be almost the same as SHE at 0 volt. It can be used as an alternative for SHE. Nowadays, electrochemical papers more often use RHE to calibrate the reference electrode of their own system as a common unit for comparison. Comparing with SHE, the secondary type of reference electrodes are popular use for the AC measurement. The future of this type of electrode is the potential stability, and this potential won't change with the small vibration of the system. This one is saturated caramel electrode, mercury salt. It is 0.24 volts more positive than RHE. However, it contains mercury. It has concern about environmental issues. Here's another one. The most used reference electrode nowadays is silver-silver chloride electrode, SSCE. SSCE is environmentally friendly compared to caramel electrodes using mercury and its salt. Its stability, reliability, and reproducibility are also sufficient. It is 0.2 volts more positive than RHE. BAS ink supplies different types of reference electrodes, including silver-silver chloride electrode, saturated caramel electrodes, and reversible hydrogen electrode. Here's the main lineup of our reference electrodes. The theoretical potential is shown here. Fundamentally, an electrode potential cannot be measured in isolation. We need to measure it relative to something else. We measure the potential of this electrode relative to RHE. Here are the devices, accessories, and reagent used in this session. We pick up one silver-silver chloride electrode, Re1BP, this time. The inner solution is 3 molar NaCl. We will show how we measure the potential of Re1BP relative to RHE. The reagent 1.2 molar hydrochloric acid is for RHE, and 3 molar NaCl is for Re1BP. To prepare RHE, we need electrolysis. Electrolysis can be made by a constant current for a certain time. Conventionally, a potentiostat has been needed for electrolysis. However, the space of laboratory and the number of potentiostats are limited. To solve this issue, we have developed a new way. We have recently released a new item, H2G1 portable hydrogen generator. By using this H2G1 portable hydrogen generator, electrolysis will be performed easily without complicated wiring and software settings. Here is the operation of H2G1. It has only one switch and one button. As you can see, the operation is very simple, easy, and clear. We will show two ways of potential measurements. One is with a sample holder, the other is with a double junction chamber. Either way will be fine. This time we'll show the way with the sample holder. Before we start a measurement, we have to do some pretreatments. We'll show you the pretreatments for the measurement. This time we'll put the silver-silver chloride electrode RE1BP into the sample holder in the measurement. First, we pour a 3 molar NaCl solution into the sample holder using the pipette. The inner solution of RE1BP is 3 molar NaCl. The potential of the reference electrodes are stabilized when the inner solution and the outer solution is the same. Then soak the sample holder into the distilled water. This method prevents the sample holder to dry. Put the RE1BP reference electrode into the REPB preservative vial, which is filled with 3 molar NaCl solution. This preservation method helps stabilize the potential of the RE1BP reference electrode. First, we have to set up the RHE by electrolysis. Here are the important points. Take care of air bubbles. Make sure to fit the O-ring into the hole of the Teflon cap of SBC2. Here is the operation of H2G1 for hydrogen generation. Pour 1.2 molar hydrochloric acid solution into half of the sample vial for the SBC2 voltammetry cell. Put the Teflon cap for SBC2 into the sample vial, then put them into the cell holder. Insert the RHE reversible hydrogen electrode through the Teflon cap for SBC2 and fit the O-ring into the hole. Insert the platinum counter electrode through the Teflon cap for SBC2. Push the disposable syringe to the top and connect the disposable syringe with a silicone tube. Pull the disposable syringe to pull up the 1.2 molar hydrochloric acid solution into the silicone tube, and nip the silicone tube into the middle of the solution by the tubing clamp. Take care of air bubbles. Take out the disposable syringe. The solution won't spill out. Connect the black cable to the RHE reversible hydrogen electrode and the red cable to the platinum counter electrode, respectively. Turn on the H2G1 and push the button for about 2 seconds and set the electrolysis time at 5 minutes. Push the button again, and 5 minutes later the electrolysis is completed. We show you what is happening inside the RHE. This is the main part of RHE. Hydrogen gas is generating along the platinum wire in acid solution by electrolysis. Here is the setup for reference electrode potential measurement vs RHE using H2G1. We will also use the TB1 thermostatic chamber to control the temperature to 25 degrees Celsius. Here is the operation. Pull out the RE1BP reference electrode from the REPB preservative vial for reference electrodes. Then insert the RE1BP into the sample holder which 3 molar NaCl is poured. The inner solution and the outer solution will be the same as 3 molar NaCl solutions. Insert the sample folder through the Teflon cap for SVC2 and fit the O-ring into the hole. Keep connecting the black cable to RHE and connect the white cable to the RE1BP, respectively. Push and hold the button, then potential measurement will start. When you set the temperature at 25 degrees Celsius, plug in the TB1 thermostatic chamber and set the temperature at 25 degrees Celsius. Put the black cable and the white cable through the upper hole of TB1 and seal the hole. And do the same procedure. Here are the measurement results. We measure the potential with the above 4 electrodes by H2G1 and the Model2325 Potentiostat. As you can see, the theoretical potential and the measured potential are not always the same. You can calibrate the reference electrode potential by using the measured value. You can also find out how accurate the H2D1 can measure the reference electrode potential. The measured potential by H2D1 are almost the same as the Model 2325 Potentiostat. Here are conclusions. It is important to measure the potential of the reference electrodes on a daily basis. If the difference between the measured value and the theoretical value exceeds 20 millivolts, you should consider replacing them. Air bubbles to destabilize the potential. It is very important to remove the air bubbles. To stabilize the potential, it is important to soak the reference electrodes in the same solution as the inner solution. H2G1 portable hydrogen generator can perform not only electrolysis, but also potential measurement without complicated wiring. We recommend you should have one H2D1 in your laboratory. Thank you very much for watching my presentation.
Thank you, Mr. Takeshi Inamori. I wish you enjoyed the lecture and the presentation. If you have any question, please feel free to contact us. The email is here. Also, you can reply from the email sent to you. In addition, in the ALS website, you can find the products showed in the lecture and the presentation, including the information about the new product. After this section, we'll move to the consultation section. Unfortunately, it was not possible to attend all inquiries for the consultation. We did something like a lottery. We sent a guidance email in advance regarding to the consultation section. Our apologies to who applied and didn't receive the guidance. We'll be contacting you, and if you require, we can analyze the possibility to book an online discussion. Thank you again, and stay safe and healthy.